Hi all. Today we'll try to cover what is OpenShift, why it appeared, and what it gives to the companies in non-technical words. Almost non-technical, as it's not easy. But we'll see. So OpenShift is based on Kubernetes that employs containers, maybe too technical for this discussion. Let's rewind 40 plus years back and switch off IT mind for a moment and start with something real. For example, from a project of building a hotel. What does a standard hotel consist of? For sure it has its foundation, its walls, windows, doors. Moreover, the hotel needs electricity, water and let's say fire service to sustain some emergency. Now let's see how a hotel is built. First, we need to create a technical task in a documented format to fix what we need. Then designers create the hotel look, architects work on technical specifics. Then the foundation is built, then stocks are built one by one, wires for electricity are laid through walls and ceilings, then finishing is done to make the cool look as designers drew on the first stage. And finally, the acceptance is performed and the hotel is open. By the way, important to note that through the process nobody thinks of building up a power plant or a fire station specifically for this hotel. Those are taken as given by the environment as it is a massive infrastructure. Why am I telling that? Exactly because long ago the process of application development was very like the usual hotel building approach. I mean that first a technical task was created, then an architecture was built along with design of the visual parts, if any. Then the task was split between the teams to develop the actual code. Only when all the teams had completed its work, a joint testing and acceptance was done to confirm that it is what the customer wanted, and then the program started to work in real life. But not all that simple. With time, programmers or developers started to think about reusing the outcomes of their work in other projects. Like how to store data, how to send a message over a network, security, and much more. A part of those recurring tasks have landed into operating system and part in so-called libraries. A set of commonly used libraries of recurring tasks form the notion of application servers. Java EE, or now Jakarta EE, and .NET are the most famous ones. Those application servers are like power plants and fire stations that hotel architects take as given. Those application servers are computer programs containing all required common tasks a developer would do in a project. They contain all common components. Application servers ran programs that were assembled by developers into a single archive. Such archive was given from developers to operations for production work. Application servers help to unify the work of teams and application support processes. But with the evolution of corporate systems, those became huge and branchy. And as the development cycle took long from requirement definition to actual implementation, the cost of a problem in the architecture was very high if found late. As well, problems that were not seen in tests might appear in production, where problem-solving process took a long time. Moreover, if a change was needed, then it might take unpredictably long to implement it. Just like if an architect wanted to change the foundation on the building acceptance phase. Operations support of those programs was not easy as well. To deploy an application server, technicians needed days and weeks. They had to take care of the created environments, update it, solve issues with disaster recovery and scale. Operations people performed constant search of errors in code they were not authors of. It were developers. Not surprisingly, this caused a lot of conflicts between developers and the supporters and long project delivery time. And then Agile era came. Agile has stopped to be technical only nowadays, but the birth of Agile was exactly in software development. The main idea of Agile was the development process organized in short cycles from requirement definition to real work, and results analysis as the basis for the next cycle. The ultimate goal was to get away from long time periods between technical tasks and the real work of the program to decrease the cost of architectural errors and to perform tasks required by business people faster. By the way, business people had to be part of the new process. Agile approaches help to significantly increase the speed of application development and changes implementation. In parallel to make development faster, developer tools were under constant evolution for team code tracking, change management, automatic assembly of programs, and others. Such automation of development work got the name of continuous integration, coming from the idea of integration of code to a single whole. But while automation and agile approaches have led to faster development and changes implementation, the operations people were unable to provide fast delivery of programs from developers to production. There were tries of deployment automation, like installing application servers and automatic configuration with scripts. Those were called continuous deployment, but those approaches were not enough, as even automation at the time of deployment took long time. The reason for that was that applications were packaged into a single whole, having all its components in one archive, or to simplify, to a file. That file is dependent on all the teams involved into the development. If the solution was big, then this archive became big or huge, having all functionality in it. Time needed to change of such monolithic application and are dependent on the slowest team in the release cycle. Monoliths were ineffective to scale, as it was not easy or possible to scale a single part that required scaling. Oppositely, all monolith applications had to be brought up on a separate instance or server or computer that was ineffective. Bringing up an application with all tasks on board was long and took minutes to hours. And finally, the developers were locked into the technology chosen. That led to using ineffective tools to solve specific tasks. What happened next? Internet availability and huge growth of people capability to be online made scalability one of the key requirements for front-end applications. Scaling and market response in weeks or even days became not enough. It just could not fly without total change of the approach and reimagining the way of operating with systems. Cloud era started when operations for standard components were taken by providers. A new approach to building systems was introduced, called microservices. This approach is interesting. It tends to create a big program from small, absolutely independent modules that talk to each other in some unified language, let's say English. Still, modules may talk internally any language they like, German or French. Teams around the modules are formed according to business domains or tasks. The teams are as small as possible. That is very important, as it totally changes the org structure of a company and brings the software development closer to business, or vice versa. This gives an opportunity to create components fast. As well, changes or even full rewrites in case of issues become fast and easy without the damage to all project, as other modules do not feel those internal changes of others speaking the same language. Furthermore, each module being small is easy to scale and may tune to number of people using it. Still, for full operations of microservices applications, companies need to have right tools. It would be really good if each microservice could be packed in a box, and this box could operate everywhere in a predicted way. As a response to those needs, containerization approaches started to evolve. Here, let's use Cloud Native Computing Foundation and Matt Butcher's giraffe Fippy and his friends. Let's say Fippy can read books and tell what it is about in the usual English language. His friend Zebra Z can type what is given, so together they can make short summaries of big libraries. The last one, Goldie, can cook to make Fippy and Z happy doing their job. Together they are a team. They can do exactly one thing that is needed by others. They can do it anywhere. So what if we put them in a box or a container? And what if they decide to go sailing as this container allows it? With this, they can do their work anywhere in the world where an ocean can bring them. They are happy going around an ocean and doing reading, typing and cooking, while they can exchange messages in common language English and results of their work. Still, an ocean is a dangerous place and storms happen, bringing friends far from each other. They lose connection to each other and become unhappy and stop working. Once, they met Captain Cube on a ship. Captain Cube proposed cabins for each of them as he sees value in what they do. Captain Cube has a big library and is not able to read it alone, and he wants to have it printed in short. The friends agree to get on the ship to be close to each other. But not only Captain Cube can get a cabin for them, being a magician a little bit, he can clone the friends as needed and let clones go off the ship anytime if their work is not needed. So if accidentally he finds a big library on some island, he can get a lot of VPs and Zs to read it fast and make short summary. When done, the clones can go their way in their containers. The story illustrates containers very well. A container has all the code programs needed for performing a task, packaged in a file called images. It performs its tasks independently and talks to other modules or containers on a unified language in IT world called APIs. Containers should be small when run. It should start its task very fast, and if not needed, it can be always stopped. This gives huge capabilities to scale to the pace of users' needs. Containers as packaged in an image can be run anywhere, like VP can do reading its book in any of the oceans. So containers appear to become the tool that can support the modern microservices architecture and make all applications cloud native. Kubernetes is the orchestration tool that can link the containers together and manage how to run it on servers that have spare resources. It is responsible to look for the number of containers running at the same time for scaling up and can stop containers when its services are no longer needed. And it can do it in a fully automated way. That is key. How the story of containers and microservices is different from running monolithic applications. Here, an analogy of pets versus cattle can help. Let's take a look at cats that live at home and cows that live on a farm. We always care about our pets. We feed them, we heal them if they are ill. Each is unique. All of them have their own names. Oppositely, a cow giving milk on a farm is usually the same as dozens of others living there. Usually, they do have numbers and no names. If a cow is ill, it is exchanged to a new cow that is same as others. Pets is an analogy to traditional environments that run monolithic applications, where operations department should care about operating systems and application servers, patch, upgrade, resolve issues, and so on. If an environment is destroyed, then recovery will take long, as all installation and upgrades should be done from scratch. Cattle is like containers. All containers from the same image are the same. So if we can bring up as much of containers as we want at any given time, and put those to a farm of servers under our control. If a container is not needed or does not work properly, then it is stopped to free up resources. A container is a black box. Operations department just runs it, and if it fails, it explicitly defines the team who knows how it works. So operations people are not that much in error looking anymore. So, the task of operations with containers is limited to setting up the right grass field to run the containers and establish that the field is always available. Developers here put their cows on the field to perform their tasks. Containers and Kubernetes give the way to deliver business domain modules of microservices applications from development to support as black boxes. Containers will be run and managed in a unified way in cloud-like environment. As containers are black boxes for operations, delivery of apps from development to production may be automated. That significantly reduces the time needed to deploy applications. Making changes is simple as well. Containers are just replaced by new versions rather than updating the old environments. This reduces the time needed to update applications and time needed to recover in case of failure. With containers, continuous integration and continuous delivery transform into a full CI/CD pipeline with automations from start of the development to production. Here it is the right place to summarize on Kubernetes and microservices. Those enable the companies to bring ideas to life faster, help to promote changes to business solutions fast, scale up and down easily, run solutions everywhere and can move between clouds. So, what about OpenShift? Coming back to the initial statement, OpenShift is based on Kubernetes that employs containers. An important fact is that to prepare the field for our cows, we need more than just Kubernetes. We need such things like storage, security, user registries, container image repositories, and other tools. If you look at CNCF open source product map, you may notice that there are a lot of projects you need to select to make up the working solution. So, to build our grass field for cows, one needs to select and integrate several open source components into one platform. More than this, if any component changes, one needs to test that all the field works fine with the new version of this component. If you find a bug and need support in an open source community, the community usually focuses on the latest release, so being always up to date to major releases is a must, but far not that easy in reality. And last but not least, and maybe the key, is that security is to be taken seriously, as open source means no guarantee from vulnerable code. OpenShift integrates all components required to being the platform. It provides customers with a ready-to-use Kubernetes environment at enterprise grade. It has all required building blocks incorporated. Support with tested updates is provided for major releases for 3+ years at minimum. OpenShift provides management portal, CI/CD tools to help developers and operations, monitoring, logging, and other components needed for enterprise work. It supports the goal of building private and hybrid clouds for cloud-native applications. Red Hat company supports open source version called OKD, that is a fully open source project integrating all the components. It is fully compliant with OpenShift, as Red Hat is the biggest contributor of the project. So this gives Red Hat customers the way to avoid vendor lock-in while using enterprise-grade system for managing Kubernetes environments. Specific attention should be taken to security topic. If we take fully open source projects, one cannot be sure that an open source library, that may be supported by a single person by the way, does not have a security issue. Red Hat checks the libraries integrated into OpenShift and provides the most secure Kubernetes environment. OpenShift runs on Red Hat Enterprise Linux operating system that is trusted by the top companies among the globe. Red Hat has created a whole ecosystem around OpenShift. It checks and validates containers of its own and partners for compliance to strong security and architectural requirements used in Red Hat. This all makes Red Hat OpenShift the best secure enterprise-grade platform for running cloud-native solutions. Thank you very much. Bye-bye.